Coming up next, we have Yilun. He is
Yeah, sorry, headphone jacking
So I should turn on audio? Audio on?
on your settings, computer settings.
Yeah, okay, it's on right now.
Yeah,
Oh,
it's
okay.
fine.
Okay. Okay, let me hide the, let me first. Okay, cool, okay, cool. Okay, thanks everyone for coming. So today I'll talk about a bit about some ideas on how we can really build a bit more generalizable embodied systems by building world models of the world in some abstract sense. So if we take a look at the current state of the art in robotics, we have these large end-to-end VLA systems that seem to be pretty flexible. So if you just ask it to, for instance, pick up the grapes and place it in a container, it's able to pretty rapidly adapt and move the containers to different locations. But I think the central issue is that a lot of these systems are actually trained on thousands of hours of data on these particular scenes. And then when you slightly even change the environment a little, like let's say you make the table a bit higher, you slightly add some new objects you haven't seen before, a lot of these systems just break very easily. So I think that at the current moment, our intelligent learned systems are very far away from what we might want, what we can imagine as intelligent robots. So if you have something like WALL-E, it's able to generalize to all types of new tasks, environments, and other agents in a very freeform way. And the question is, how do we really get to robotic systems that can likewise be as generalizable or general purpose as the ones that we see in sci-fi movies? And I think that this is a lot more challenging in the robotic setting than it is in many other of the other settings we consider. So if you consider something like natural language, there's so much text data on the internet. And as a result, the training distribution of natural data we get is roughly covers the entire distribution in which we may want our system to operate over. In contrast, in robotics, we have relatively little data. And really, the data only captures certain specific instantiations or specific tasks or environments that you have the data over. And your goal is really to get some type of system that can take data from these very narrow training slices and really get it to be able to generalize more systematically across the entire set of scenes that the robot may encounter. So in this talk, I'll talk about this idea that instead of trying to formulate decision-making as the end-to-end prediction problem where we directly try to predict actions, we should instead actually formulate decision-making as about building some type of model of the world and really formulate decisions as some type of inference procedure on top of this model. So in this talk, I'll talk about how this idea of learning a probabilistic generative model of the world is a way to really get towards this goal of more general intelligence. And first, I'll talk a bit about how you can really use this world model to predict and plan adaptively for new objectives at test time. And then I'll talk about how we can really construct them in a really structured way so that we can generalize to areas we don't have any training data over. And I'll talk about a really particular instantiation of probabilistic generative models, generative world models, but there are other ways to also instantiate these. So let me give an example. So let me consider, so normally if we have a task such as climb up the stairs, typically we're trained a neural network to taking that image observation and directly output a discrete action trajectory. And this is really great when your training and test distribution are exactly the same. So you're in the exact same environment that you've been in the past. But as what often happens in the embodied environment is that the environment will change over time. Suddenly there'll be obstacles in front of you. Maybe your battery is running low. And when you just have a neural network that simply outputs a single answer, you don't know how to adapt or change your system to these new constraints. And so one idea is that you can really get a much more adaptable system by, instead of having the system directly output an action, you can instead have the system output what its preference is over every single output, every single action trajectory in the environment. So you have a system which takes in an action trajectory as well as an image, and it simply outputs an energy or likelihood or a utility function for how good that action is. And now under this system, what you want to do to infer an action in this environment is that you just simply search for an action that minimizes your energy. So why would I make a simpler problem into this really complicated one where I want to really find these trajectories that minimize energy? Well, the idea is that this framework allows you to really easily adapt to new constraints. So now let's say I have my original constraint that I want to climb up the stairs, but now I have new constraints on battery life or safety. What I can do with this more implicit representation of the task is I can take this energy function for the first task, and I can combine it with this energy function I construct for the second task, such as ensuring safety. And now by taking this new energy function that I get, I can simply optimize for an action that minimizes both of these energy functions. And this allows you to adapt your decisions to these new constraints. And that overall high-level idea is that by building some type of model of the world, now you can do some type of search process, and the search allows you to adapt. Cool. So that's the first idea about trying to use world models to adapt to new tasks. So the second idea is that when you consider building these models of the world, you can actually often build them in a very compositional manner. So you can build them in such a way that the models can generalize the areas that you don't necessarily have data over. So what does this mean? So what I mean by this is that we can, so let's say we want to learn a probabilistic model P of X over like how the world operates. What we can do is we can actually factorize the distribution we want to model. So instead of learning a distribution directly over all the variables of interest, you can learn factors that capture parts of the distribution. So maybe you have one model that models the interactions between language and videos, another one between videos and actions, but essentially you can represent the complex distribution over variables as a product of these smaller subfactors. And what this assumes is that you assume that your data is somehow independent. So somehow maybe two factors don't really affect the other two factors. But by making this assumption, now if you have data that's relatively that is relatively narrow in distribution, what you can do is, as long as each of these factors are in distribution, the product can now allow you to cover the entire or cover a larger part of the data distribution than what you originally had. And this really kind of reflects the natural structure of the physical world because many different factors are naturally independent with respect to each other. And in practice, though, when you assume some type of factorized form for the distribution, you are making some independent assumptions, so you do make some errors. But you can imagine actually fine-tuning the approach or adding additional factors so that you can more accurately represent the distribution that you care about. Okay, so that was just a general idea about like two ways of how, like why you should build models and how you can really build them in a compositional manner. Now I'll talk a bit more about some details of this framework. So first I'll talk about how you can really implement this idea of compositionality or models using energy-based models. Then I'll talk about how this compositionality can be used for downstream decision-making. And finally, I'll talk a bit about how you can use this approach to really do reasoning and solve new tasks that you haven't seen before. So first, let me talk a bit about this idea of energy-based models. Building on the example I showed earlier. So when we talk about energy-based models, what we want is we want a neural network such that when I specify a constraint, for instance, I want a red truck energy function. If I give it an image of a green truck, the energy is high. And if I give it an image of a red truck, the energy is low. And essentially, this energy function recovers energy landscape across the entire space of images. So that all images that are red trucks have low energy, and all other images have high energy. And then this energy function implicitly encodes a likelihood distribution, or it can encode many different things, but it can encode a likelihood distribution by using the Boltzmann distribution e to the negative energy. And one way to interpret this energy function is essentially a verifier over the space of generations. So the energy function is essentially your verifier, where low energy outputs correspond to high verification score. And so once you have this energy function to generate from this model, what you do is now you run some type of iterative process or procedure where you can follow the gradient of the energy function plus some Gaussian noise. And what it ends up looking like is it looks pretty similar to the diffusion process. And I'll talk a bit about the similarities next. But essentially, it becomes that this iterative gradient descent procedure allows you to gradually generate an image. But the benefit of having this type of iterative Langevin sampling procedure to generate things in comparison to explicit models like GANs is now I can form any type of new energy function I want. And now I can use the same sampling procedure to enable you to generate from that new distribution. So it allows you to trade off the generation speed for flexibility. So typically, the typical way that you train energy-based models is to use some type of contrastive loss. And what we do in this contrastive loss is that you have some ground truth data. You try to decrease the energy of that ground truth data, and then you draw some samples from the energy distribution using the Langevin sampling procedure I talked about earlier. And then we use that to essentially increase the energy, or like we take the samples that we draw from the model distribution and increase the energy of those samples. And the idea is by contrastively doing this for a while, I'll give a graphic illustration in a bit, and you essentially get a model that has low energy exactly at the ground truth data. So energy-based models are really an old class of generative models starting from the 1980s, 1990s. In early 2019, we illustrated how you could use some type of combination of Langevin dynamics and replay buffers to really scale these to modern image tasks. So here's an illustration of what energy-based models look like. So at the beginning, there you have some type of flat landscape so that both red trucks and Gaussian noise all get assigned the same flat energy. Then what you do is you just decrease the energy of ground truth data. So now you have a landscape where red trucks have lower energy, and while we're just pulling up the energy of a sample you drew from the landscape, which is Gaussian noise at the beginning. So now you have a better shaped energy landscape. And if you run optimization again, you'll get an image that looks a bit more like a noisy red truck. And then you can repeat the procedure where you decrease the energy of red trucks and you increase the energy of the noisy red truck. And you just repeat this procedure until you only have low energy exactly at the images of red trucks. And at which point you decrease the energy of red trucks and increase the energy of red trucks. And that's how you converge to your final energy distribution. So the training procedure ends up looking pretty similar to GAN. And if you actually read the first GAN paper, it actually talks about how this is inspired by energy-based training way back in the day. So one nice thing about training energy-based models is in addition to this contrastive training procedure, another way that you can also train these energy-based models is directly using a diffusion model. So this is a sampling procedure we proposed in, I guess, late 2018, early 2019. And you can see that you kind of have this gradual noising process where eventually you get a ground truth image of scenes where the quality is pretty low. So a year or two afterwards, I guess there was some score-based models, and then there was diffusion models. And essentially, they adopted the same Langevin sampling procedure, where now you train the denoising function to basically estimate the gradient of the energy function. So you can interpret diffusion models as a type of energy-based model, where essentially the denoising function is just the gradient of the energy. So this allows you to compose diffusion models like you could compose different energy functions. And I always also use that for quite a few examples in the talk. One big difference between diffusion models and energy-based models is that diffusion models learn this gradient, but not the actual explicit objective function you want to optimize. But you can actually change the diffusion training procedure to also explicitly learn this energy. So the benefit of this energy interpretation is this idea of compositionality or generalization at test time. So as another example, if I have this red truck energy function and I directly optimize it, I get an image of a red truck. But what I can do is I can take a red truck energy function and I can take a desert energy function. And at test time, I can simply add the two energy functions to form a new energy function. And now if I optimize this new function, now I get an image of a red truck in the desert. So the power of this abstraction is that now I can combine multiple energy functions to form images with new attributes. And in general, by combining the energy functions in different ways, you can combine different probability distributions together. So if you have one model for a P1 of X, and a separate model for P2 of X, you can draw samples. By combining the energy functions, you can draw samples from the product distribution P1x times P2x. With a separate energy operation, you can also draw samples from the mixture distribution P1x plus P2x. Or you can, by taking one energy function and subtracting the other one, you can finally draw samples from the distribution P1x divided by P2x to the alpha. So why is this useful? So the nice thing about doing this is that it allows you to really repurpose generative models to construct more complex scenes than maybe the ones they've been trained on. And an example of this, assume we have a pretty simple generative model. So we've trained it on single noun phrases. So we've trained it to generate a scene of a horse or a sandy beach, grassy plains or sunny. What you can do is if I want to have a more complex textual description or generate a scene based off a more complex text description, for instance, I want a horse that is either on the sandy beach or grassy plains where it's not sunny. You can roughly parse this description into a set of logical operators, which you can convert into like the composition of probability distributions. So you can say that drawing the sample from this complex text description is roughly similar to drawing it from a distribution of images given horse multiplied by the distribution of the mixture of sandy beaches and grassy plains divided by the distribution of the image being sunny. And you can actually, and this is what you get in terms of actually composing distributions. So if you have a distribution for a horse, by repeatedly, recursively combining these distributions, eventually you can get a scene where you have a horse, where it's either a sandy beach or grassy plains, which are the top two rows, where it's also not sunny. Okay, so that's an example of how you can use this idea of composition to really generate these scenes that are more complex than the ones you've seen before. You can also use this composition of energy functions as a way to understand scenes that are more complex than the ones you've seen before. And the idea here is now, let's say you have an input image, for instance, this image of 3 objects. Now what I want to simply find the composition or sum of energy functions such that the likelihood of the image is maximized. So this is similar to analysis by synthesis, but essentially I just want to find the number of energy functions that are composed as well as the corresponding latent parameters of the generative model so that the image is most likely. And what we find is that this approach where you use this compositional approach to perceive images, well, if you train it on images of 3 to 5 objects, we find that it's able to quite accurately determine the locations of the 3 objects. So here we just infer 3 for the top example. We just infer 3 energy functions where each energy function is conditioned on the position of 1 object in the scene. But the benefit of this compositional approach is that you can do generalization. So we can take the same model trained on 3 to 5 images and now give it 6 to 9 images. And what we find is by simply inferring the parameters of all 6 to 9 energy functions, we can actually get a model that can infer the positions of every single object. So this allows you to much more accurately generalize to more complex scenes. And then you can also change the scenes. So you can actually change the material properties of the scenes and lighting. And then we find that because you're generatively modeling the scene, and also tends to be pretty robust to these changes of lighting conditions. And as a final note, you can also use this to actually infer the number of objects in the scene. So you can just try to describe the scene with 3 objects. Let's say you have a scene with like 5 objects. You can try to describe it with 3 energy functions, 4 or 5. And you find that the one that minimizes energy is exactly the ground truth number of energy functions. Cool. Okay, so that was just a brief introduction on this idea of energy models and how you can compose them to both generate and understand more complex scenes. So now I'll talk a bit more about how you can use this for decision making or actually controlling a robot. So to do this, we can actually just represent decision making, like either planning or reinforcement learning, is simply composing several objectives or energy functions. So you can have one energy function that just has low energy for all valid trajectories in the environment. And then you can specify, and then you can just make the objective function you want to optimize, whether it's your goal, a value function, or test time constraints, as a separate energy function over the trajectory. So trajectories that maximize your objective function would have low energy, and otherwise they would have high energy. And now if you take these 2 energy functions and compose them, you can form a new energy function that essentially encodes the constraints or the decisions you want to make in this environment. And by running optimization, you can now do different types of planning and reinforcement learning. So let me actually give a couple more concrete examples. So first, let me talk a bit about maze planning. So to do maze planning, I can train this first energy function that just learns an unconditional distribution over different trajectories in the maze. And what I can do is I can construct a second energy function that I just explicitly hand construct, which says that your start state and go state must be the specified values. And if they're not the specified values, then energy is infinite. And only if they are the specified start and go values is energy low. So now if I compose these 2 energy functions together, I now get a new energy function that has low energy exactly at trajectories that have a fixed start state and go state. And in practice, to actually implement this, you just simply, during the optimization process, fix the start and go state, or constrain it to be a particular value to instantiate this optimization. But what you can see is that this actually enables you to get a zero-shot goal-seeking policy. So here we have 3 examples where on the environment on the right, we just trained an unconditional model for trajectories of up to length 512. And these trajectories are random trajectories for an RL agent. So they actually loop around all over the place. But by fixing a start state and go state and now running the sampling, we can actually get trajectories that go from a particular start state to go state. So this allows you to effectively plan in a long horizon context. And we compared our method with a couple offline reinforcement learning techniques. This is a pretty long horizon decision-making problem. So it's hard for these models to perform well in this setting. And we also find that the model works well both in a multitask and single task setting because it requires no training. You're simply just adding the constraints. So more generally, you can also take the same energy function for different trajectories. And you can just define a second energy function that's just that just estimates a reward at every single state. So now you can formulate your optimization problem is just finding states that are consistent on the first model so that they satisfy dynamics while also maximizing your reward function. So this is an inference-free method where you just try to optimize both of these functions. But what we find is that this type of inference-free method where you're just doing planning on the dynamics model actually performs very similarly to the state-of-the-art offline reinforcement learning techniques. So here we can take our approach, which is the yellow one, and we can actually compare it to the state-of-the-art offline RL techniques, and we find that it performs very comparably, suggesting that you can actually just use this composition as a way to do reinforcement learning. And finally, when you're combining these energy functions together, they don't actually have to be over the entire trajectory. They can actually be over chunks of your trajectory. So this is important when you really want to solve. So let's consider this like really big maze. And now I want to form a trajectory that goes from the start state to go state. But really, because it's such a large maze, you haven't seen any trajectories that actually go from the start state to go state. But you've seen chunks of trajectories that maybe go from one location to another, or a second location to a third one. What you can do is by optimizing energy functions over chunks of the trajectory. So you have one model that's just this part of the trajectory, a second model that's the second part. If you optimize a composition of many chunks, you're able to recover overall trajectory that can actually go from your start state to go state. So let me maybe make this a bit more concrete. So here we have another environment where this is an ant maze environment. So we have a random RL policy or a random policy that gathers this data. So in this data, the model, the ant just locally moves around. So it isn't able to actually go from one location to another. But we can now take the segments of the agent moving locally around, and we can stitch each segment together. So now we can initialize the agent at the start location, which is shown in green, as well as this goal location that's red. And by stitching these chunks together, we can actually get an overall plan that is able to go from the starting blue state to eventually to the final goal red state. So by stitching different parts of trajectories together, you can actually construct these trajectories that can accomplish much more complex tasks than what any of the behaviors of the agent initially had. And another thing you can do is you can also use this type of energy optimization framework to actually combine multiple different foundation models together. And the idea here is, well, first, let me actually give some motivation on why you might want to combine several foundation models together. So let's say I want to do an open-ended problem, such as making a cup of tea. Well, to solve this task, it turns out that different models give you different information for solving this task. So if I want to solve the hypothetical task of making a cup of tea, a language model can give you a lot of high-level information. So it can tell you to first look for a tea kettle, to heat the water, or to find a tea bag. A video model can tell you a lot of detailed visual information. So a video generation model might tell you this is how you actually pour a cup of tea. But again, the video model can't tell you the things the LLM knows. So the video model can't tell you how to reason or the steps, high abstract levels, steps needed to make a cup of tea because it only knows the local visual information. And finally, if you have some type of ego-centric action model, well, that model is able to actually tell you how to control objects and actually how to pick up things. But again, it doesn't have any of the mid-level information about visual, about the visual motion or the high-level information in the language model. So none of these models by themselves are able to really accurately solve this task. But what you can do is you can actually take the product of the distributions, which corresponds to adding the energy functions together to combine all the information across all three of these models. So what you want to find a text plan, an image plan, and an action plan that is high likelihood across all three of these models. So you want to find a text plan so that according to the large language model, given your final text goal, this is a plausible plan for solving the task. At the same time, you want to find an image plan such that when the video model is given the starting image, as well as the corresponding text plans, it can actually imagine a video plan for solving this task. And finally, you want an action plan so that given the really detailed video plan, the model can actually imagine a series of of continuous actions that can allow you to accomplish the video sequence. So if you can actually find a plan that satisfies all the constraints encoded by all three of these models, then you can solve this task. And the idea is this trying to find a set of trajectories that optimizes all three of these models corresponds to another energy minimization problem. So you want to find a text plan, image plan, and action plan that just jointly minimizes all three of these energy functions based off each model. Where here, each energy function is just the likelihood of the corresponding model. And it turns out that this type of optimization is pretty simple. So the way you do it is you just sample a couple of language plans. You choose the language plan that the video model is able to best generate a video for. And at the same time, you sample a bunch of video plans and you choose the one that action model is able to best select for. And in a sense, that loosely optimizes all three of these models. And here's a pictorial representation of this. So if I have a goal, stack a red block on a cyan block and place a brown block to the right of the stack, the language model can't actually see the visual scene. So it will say something like place the cyan block in the brown box, which is a plausible instruction given the original goal. But the issue is there is no cyan blocks in this environment. So the video model isn't able to construct a corresponding video generation. But you just repeatedly sample until you get one that the video model can do, which in this case, it says place the white block in the cyan bowl. And now the model is actually able to pick up the white block and put it in the cyan bowl, because this is a plausible one that you can actually imagine given the starting state. So if you try to jointly optimize both the language model, video model, and action model so that all three can get a consistent plan, you can actually combine them in a zero-shot way to accomplish this overall task, where we want to stack a red block on top of a brown block and place a yellow block to the left of the stack. And when you actually combine these models, you don't actually have to combine the models using their likelihood. You can also have the models define their own objective functions. So what I mean by this is you can also actually for when you're optimizing the language model, or when you're trying to optimize a language plan and an image plan, you can actually use a VLM to measure the consensus between the image and language plan. So if you have a text instruction, put the fruits in the top drawer. If you have an intermediate video plan where you're picking up the banana and simply dropping it, then you can use a vision language model to also tell that this is a bad image plan given the language plan. And so if you use a vision language model as some type of intermediate progress estimator, so that when you actually open the cabinets, you make more progress, then you can formulate this type of optimization process between all three models as a tree search procedure. So you have a starting image, and then you have a goal, put the fruits in the top drawer. And you simply just expand different possibilities. So you will first generate two language plans, either opening the top drawer or placing the banana in the top drawer. And you just simply you synthesize different image plans using the video model and use the VLM to select which one is the most promising. And you can just repeatedly do this in a tree search procedure. So you just repeatedly sample different possible actions. And then you do it until you finally get one that according to VLM appears to solve the entire task. And this allows you to get a very detailed visual plan for solving this task by rolling out both the video model and language model. So we did this so we took a off-the-shelf vision language model, off-the-shelf video model, and action model, and we combined them in a zero-shot way. And we found that the zero-shot way eventually allowed us to accomplish this task, put the fruits in the top drawer. So here, none of these models were explicitly trained on this task, but this combination of planning and then using an action model to convert the visual plan to actions allows you to zero-shot solve this task of placing all the fruits in the drawer. And here's another example of this. So here we have a bunch of objects on the table. And again, by running this type of energy optimization across all three of these models, you can dynamically generate a language plan of moving objects around. And then you can get this corresponding video plan where, starting from this image, you have this completely generated visual plan of how you should move objects so that they can become a line. And so this was all generated from the first image. And then both the language plans as well as the video plan are autonomously generated. And you can also make this procedure and use it on a real robot. And so here's the corresponding real robot execution of making a line. And what we overall find is that by combining several foundation models together, so here we're combining a vision language model, a video model, and an action model. But by using this type of composition between these models, we're able to generalize much better than a single large video model, a single large end-to-end policy, or hierarchical methods where we don't have planning. So just having these separate having more of this model and this planning can allow you to solve more long horizon tasks. Great, so those were a couple illustrations of how we can use this type of energy combination to really enable us to do planning. So finally, I'll talk a bit about how this idea of combining these energy functions, or like these implicit models of the world, can allow you to do more reasoning and solve more complex reasoning tasks than the ones you've been explicitly trained on. So in general, when you're solving a reasoning task, for instance, if I want to find the sum of two matrices, you can formulate it as an optimization problem. So you can have an energy function that takes in these two input matrices, and it defines energy landscape over X, where X is the possible solution. And by optimizing over this energy landscape, you can get a prediction that solves the reasoning problem you care about. And now in this setting, the energy function is basically a verifier, where now it's just like checking how good a solution is, and you're just using some type of inference time search procedure to find a solution for solving this task. And the benefit of this type of iterative energy minimization procedure that solve prediction tasks is that now you can, to use more steps of computation, you just simply try to run more steps of optimization to minimize your energy. And what we find is that as you run more steps of optimization, you smoothly get less and less error, where we train this model on graphs of size 10, and we're able to, by running more steps of optimization, generalize it up to graphs of size 30. In contrast, if you just try to use a traditional method for scaling test time compute, like a recurrent neural network, we find that it actually explodes when you try to use these much larger graphs that hasn't been explicitly trained on. So in general, this operation of energy optimization, there's some more numerical numbers, but overall, the idea of optimizing energy functions allows you to make reasoning correspond to verification, so it can generalize a little better to harder tasks. But the nice thing about this idea of compositionality that I've talked about is that this idea of compositionality actually allows you to solve even harder reasoning tasks than the ones you've seen before. So here we want to color this graph so that every two nodes with an edge on it. So whenever you have two nodes that are connected by edge, we want to make it so that each node is a different color. So to solve this complex task, we can simply just learn these models for different parts of the subparts of the problem, and then we can formulate solving the entire tasks as just optimizing the answers so that every single subproblem is minimized. And what we find is that this is a pretty powerful method to allow you to solve much more complex tasks. So let me give two examples. So in the first example, we trained an energy function so that it just learns to assign a queen on a row of 8 row of 8 squares. And on the second, we trained a model to just color two nodes given an edge. And now at test time, by combining multiple instances of these models, we can actually now fit the objects so that they satisfy the 8 queens problem, so that each object is not colliding with each other, or we can compose these models to color this graph. And what we find is zero-shot composition of these models actually allows you to, at inference time, to solve the 8 queens problem 97% of the time by simply just optimizing the constraints across each diagonal, row, and column. And we can also do this with SAT problems. So you can train these models on SAT problems consisting of 20 variables and 91 clauses. And by composing models across more clauses, you're actually able to generalize and solve harder problems with 50 variables and 218 clauses. And actually, the baselines we compare to here are more combinatorial optimization techniques. So it's interesting that this type of energy formulation actually allows you to solve these tasks. And you can also use this to solve more complex geometric rearrangement tasks. So here we want to solve a problem with triangle packing. So we want to pack a set of triangles to arrange them on a square. What we can do is you can just learn these pairwise constraints. And by composing these constraints, you can solve triangle packing problems with more number of triangles. You can also use this to arrange objects qualitatively in a grid. You can also use this to arrange objects subject to geometric constraints. Or finally, you can use this actually to solve new robotics problems. So you can formulate robotics manipulation is simply satisfying a set of constraints on picking up an object, making sure you don't collide with other objects, making sure you reach the goal, and so forth. And this allows you to do zero-shot 3D object packing. And a final thing is that this type of optimization procedure can also be combined with large language models. So when you have a large language model, you can actually treat the large language model as a verifier, where the verifier is now the energy function. And given a question, what are the roots of this function? You can simply generate many different possible answers. And then you can just use the energy function, you can just combine a bunch of verifiers, ask them to check each part of the solution. And this allows you to select the answer that is most accurate. So here's an example of this. So let's say I have a problem where I give you this continued fraction, and I ask you to represent it as an improper fraction. What you can do is now you can just have multiple different language models, which are, some of them are Gemini, some of them are GPT-4o, but you can prompt them to check the answer in different ways. So one of them can just directly say, is the answer correct or not? Another model can say, is the unit conversions correct? Another one might say, is it logically sound? Is it generally correct, or is it like mathematically correct? So you can just prompt different models, which are now your energy functions, to verify different aspects of the solution. And this allows you to get an overall verifier that's much more powerful than any individual model. And what we find is that as you increase the number of verifiers and then as you increase the number of generations, you're now able to gradually improve your performance across each of these benchmarks. You can also compare performance as you generate many more output solutions. What we find overall is that because you're combining many of these verifiers to select your right answer, you are able to gradually increase, you're able to get a much higher peak performance than you do for either the self-consistency or just directly prompting a language model to select the right answer. So overall, I guess I've talked about in this talk this idea that if you can learn some type of model where the model is represented as this type of energy function, and where you can actually build these models much more compositionally by combining different pieces together, you can get a system that can solve much more complex tasks than the ones that you explicitly have data over. Thanks everyone for listening, and happy to take any questions.
So thank you. Nice stuff. This is nice. I mean, you're a fan of optimization, and so am I. And it's really nice to hear these words because when I started my PhD, it was like this, Boltzmann distribution and everything. And so I love optimization too, but one problem with it is that it's really hyperparameter, tuning hell. Like it's true, it is really compositional, but actually, how do you deal with that in your problems?
Yeah, so especially towards the end, as you compose more of these models, optimization gets increasingly harder and harder. We have a set of optimization techniques to try to make it a bit better. What we do is we will instead of optimizing one particle, we'll optimize a bunch of particles at once, and then we'll reject or backtrack on solutions to make sure that we can get lower energy solutions. But yeah, it is definitely the case that with this energy formulation, the optimization gets much harder. I think it's a little easier with neural networks than it is with traditional hard constraints because the neural networks give you more continuous gradients and they tend to have smaller local minima or like less local minima. But it definitely is the case that, yeah, you still have to spend a lot of effort optimizing.
I actually think there's the optimization part too, but this is the scaling of the weights, energies actually.
Oh, okay, yeah, that's also true. So the other issue is that you also don't know what the magnitudes of the models are. So like, how do you choose the right weights so that you can satisfy the objective you really care about? So again, we do a decent amount of tuning. One thing you can do is you can actually train these models together at once. So let's say you know that this problem is specified out of these weights. So you can just say the solution is generated by composing all of these energy functions, and the models can implicitly then figure out the right coefficients to compose with. So if you do know some of the problems you want to solve, then you can kind of discover the right set of weights. But otherwise, yeah, you do also have to spend time tuning those weights.
But doesn't that kind of undo the composability because you're jointly training them?
Well, so I guess it's if you're jointly training them, that you can still at test time be able to compose more instances of the model. So let's say you know that this problem is represented by the composition of module A 3 times and module B the 4th time.
Subset of those combinations you could do.
Yeah, well, so you could imagine that you can train with three of A and 1 of B, but then at test time you can still do 5 of A and 2 of B. So you can still compose in new ways.
Okay, this is kind of related to actually this problem. The nice thing about the energy models is that you're kind of getting away with the normalization term, So that's a really interesting analog between like the diffusion models or flow matching versus like this type of diffusion. It's like learning the score function, it is just the gradients, but then you don't actually have this normalization issue. If you actually went for the likelihood, you have this normalization issue, which you kind of go away by making it into the energy by putting it into an exponential with some kind of weighting factor. So like, what's your pros and cons? I'm sure you've worked with both, and like, so are you like a lot of things like just score functions. Like, what are your thoughts?
Oh, okay. So there's a question of whether it's score function or energy function, or
you're saying, right? The relation to the diffusion model is that like diffusion models actually learn the gradients as opposed to you're actually learning the energy function. Yeah. To me, that's like great. The score function versus actually learning the distribution.
Yeah. Oh, interesting.
The difference is actually in the normalization.
Okay. So I actually think so with these energy functions, you again don't have to learn the normalization constant because you just have e to the negative energy.
So it's like unnormalized.
Yeah, it's unnormalized.
Basically, it's kind of similar to the Score function.
Yeah, so I think these are, I think the energy function is very similar to the score function. I think the one nice thing about the energy function is you actually know how well you're optimizing. So with the score function, especially as you compose these models together, right, you actually don't know which one you're optimizing, but now you actually know how well you're optimizing, like in the sense that you can compute the energies for each thing you're combining. And now you can choose which one to add more weights to and so forth. So I think the energy function actually allows you, and you can also combine these models in interesting ways. So if you want to do, I want to generate either concept A or B, well, I can now take the energy to select the one that's lower, and then I can choose that one. So it gives you some more freedom in combining and optimizing the models.
Okay, I have one more question. How do you actually get that likelihood from the video models or the LLMs?
Yeah, so
Or machine?
yeah. So for the video models, you can just I guess you can just try to compute the elbow. So you can just add different amounts of noise to the inputs, and then that can be. And then for language models, I guess you can just compute the likelihoods explicitly.
All right, thank
Yeah,
you.
thank you.
Hi, hello. Great presentation first off. Yeah, so I guess I was struggling a bit with so like I find this sort of paradigm really interesting for kind of thinking about these problems, but I was struggling with some of the, I guess I call it practical motivation, specifically regarding the compositionality. So like I guess this depends on kind of the problem, but like for like robotics, for example, like if you're representing these sorts of different energy functions as kind of like constraints, then by sort of defining kind of like the weighted sum of these energy functions in your compositionality, you're kind of implicitly defining kind of like the trade-off between each of these constraints essentially. And I guess I'm wondering like if you already have this like kind of like really well-defined trade-off between like the different constraints you are kind of like running on that test time, you know, why not just kind of like optimize upon that combination like in your first pass compared to doing this sort of like test time optimization machine learning?
Yeah, I think so. I think my overall point is that like when you're a decision-making agent, you don't know a priori during training time what objectives you want to optimize that test time. So the road is always changing. So you will always find yourself in a setting where like maybe you have a new combination of obstacles, maybe you have more obstacles than you've seen before during training, maybe your objective functions are different than the ones you've seen before. So the idea is that with this energy approach, you're actually doing the test time. You're kind of doing the test time sampling, but it allows you to generalize flexibly to new objectives you haven't seen at training time.
I think so. So it's kind of like increasing like test time adaptability.
Yeah, basically, yeah. And I guess the claim is that for most embodied agents, most of the time, your decisions in the world are different ones than the ones you've ever seen before. Like because the world is so varied in terms of objectives, in terms of obstacles, and so forth.
How like this kind of ties up with one of the prior questions, but like given that again these models don't really have like units assigned to their energy values, like how would you like specify at test time what these trade-offs would be like? Like would it just be like kind of trial and error or kind of like opposite? I guess like how would you assign these weights basically?
Yeah, so the models don't have like well-defined magnitudes. So yeah, you have to choose the weights. I mean, in practice, we usually set the weights to be 1. It usually works okay. But like idea like maybe like if you're like I guess there's this like if let's say you're in a new environment, you don't know like you can like you can kind of do like a few shot learning almost. Like you try it once with certain weights, it doesn't work. You try to increase your weight again, it works, right? But like in a sense, this like optimizing the weights of the energy functions can be a way of like few shot learning, and that might be more efficient than like trying to fine tune your network to solve this new task.
I see that. So you kind of change it from like retraining the whole network to kind of just changing these weights.
Yeah, changing these weights. Yeah, so it becomes a more space. Yeah, thank you.
I thank you for your presentation. I'm a big fan of your work. Just want to ask about something on the kind of the computational complexity one, because for the energy-based model, you have to do the long form dynamic to do the sampling. And I know there's like a big like kind of related to like diffusion model, but for diffusion model, there's more and more like speeding up kind of techniques. You have like the one-step diffusion or DDIM or consistency model. So can you shed some light on for the energy-based model? Is there any possibility to speed up the sampling process, for example, to like 1 or 2 step of sampling type of?
Yeah, so I mean, it's basically, I guess, energy perspective is just like how do you optimize the objective, right? So what you can do to speed up the energy objective is, again, you can imagine you have some type of amortized generator that just predicts initial guess, and then you just do a couple of steps of local gradient descent to find a better minima.
I see.
So
it's kind of like landing at everything near your target.
Yeah, near your target. And I think this is roughly how all the distillation things kind of work anyway. So you're like just loosely trying to make your early steps like basically land where your end steps go. So you can do something very analogous with these energy functions. Yeah, thanks.
Thank you so much to our speaker. And if there are no other questions, let's close the workshop. Thank you so much.
Yeah, thank you.